Good day. This is a continuation of the educational video series for plastics professionals. The SPE Extrusion Division presents an introduction to rheology focusing on troubleshooting. In this video we'll develop quantitative rheology functions relevant to extrusions in polymer processing for both Newtonian and Power Law rheology. Our goals are: develop a Newtonian viscosity function, add temperature effects, develop a power law viscosity function, add temperature effects, and then show how we might be able to use these functions in our troubleshooting or process development. Our goals are therefore to develop a quantified Newtonian viscosity function, to develop a polymer power law viscosity function, and then to show you how to use these in your mathematical analysis for either troubleshooting or screw or any other type of development. We're going to look then at Newtonian functions, which viscosity is constant at constant temperature, and power law functions where viscosity is a function of the shear rate and the temperature. This is a Newtonian viscosity definition. It's equal to the shear stress divided by the shear rate, and we have demonstrated how these different functions come about in a previous video: shear rate, shear stress, viscosity. For Newtonian at 543 degrees K, the viscosity in this particular system is a constant at 1.268 times 10 to the 5th Pascal seconds, and this is of course at a fixed temperature. Power law constant temperature and viscosity function at 543 K is more complicated since it's both a function of shear rate so the power law function, viscosity function, has a constant and a slope. The power law of viscosity is defined as a function of shear rate with a power law slope of n-1. MPL is the power law constant. If n is 1, then there's no shear rate effects, and it essentially is MPL is essentially the Newtonian viscosity. If n is between 1 and 0, then the viscosity acts like a power law fluid. We've been talking about this particular viscosity function, and for the Newtonian system we developed a Newtonian function at this temperature. We're going to talk about doing the same thing for a power law function, which would be along this line. So first we need a set of data, and here we have the shear rate data and the viscosity data. So we can do a manual process just like you did when you were doing algebra in high school to develop the function. Here we have our power law function. We linearize it by taking the natural logarithm of both sides, and so we end up with a power law linearized equation that looks like this, which is a function of the power law of viscosity and the shear rate. The slope, as we learned back in algebra, is the rise over the run. We put in the viscosity at 10,000 reciprocal seconds and the viscosity at 1.1 reciprocal seconds from here, and we end up with a slope of 0.796, which is n-1. We then substitute this back into the equation, and we end up with MPL is equal to e to the 11.227. This is an approximation and could be used in the laboratory or when you're out in the field, but it's only two data points. Only two data points were used, and it's not going to be phenomenally accurate. So if we start out with our power law function again, and we use that complete data set we talked about before, we could recall this power law function. We really would like more accurate constants than we did in the slide before. So we use regression analysis on the previously developed data set. We linearize the equation as we did before, and you can see that below. Running regression analysis, log shear rate versus log viscosity. I use MathCAD. Most people would probably use a spreadsheet. Regression constants. MPL is 11.55, which is slightly different than the one we got before. And the regression slope, n-1, is 0.225, which is also different than we got before. These two are much more accurate than the one we did linear by hand. So now we have two functions at 543K. We have the Newtonian viscosity, and we have the power law viscosity as a function of shear rate. And we can use these two functions to approximate both ends of the viscosity curve that we started out with, as you can see here. What we'd really like to have, though, is to be able to see the effective temperature. And here we have our friendly little styrene viscosity data set at 3 different temperatures. We're going to then use these data to develop temperature relationships for both the Newtonian and power law relationships that we've just developed, so we end up with a general purpose relationship over the whole shear rate range. So we go to 2 different shear rates, and in this case we go down into the Newtonian region, which is a shear rate of 0.01, and we use temperatures at 503 and 543, and from this we pick off two viscosities. Then we go out into the power law region at 20 reciprocal seconds, same 2 temperatures, and we get the 2 viscosities at that temperature and shear rate. So we're going to look at for the Newtonian system, we're going to look here at the viscosity at a reference temperature Ti, and eta T is a temperature dependent viscosity, and Rg is the ideal gas constant. When we do this, we take we look to solve for delta E over R, and to do that we've linearized the temperature part of the equation, and what we end up with is an activation energy of 17,940. And then this is put into the previous viscosity equation. We end up with, and we use our reference temperature and our reference viscosity that we used previously, and we now have a temperature dependent viscosity, Newtonian viscosity. Notice that this is fairly high, 17,000. So now we're going to do the same thing with the power law viscosity. Here we're going to go at 20 reciprocal seconds, which is well into the power law region, and again we're going to use 543K as a reference temperature. We do the same type of Arrhenius type of function to get the activation energy at the 2 temperatures and the 2 viscosities. You notice here and here, and this gives us an activation energy of 6,440 K, which is only about 1/3 that of the Newtonian viscosity activation. And we can put this into the equation, and here we have our viscosity dependent, our temperature dependent power law viscosity at this particular shear rate. So we now have our complete Newtonian viscosity curve, and now we'll go back and we'll put in the constants that we found before, since the slopes of these lines are all the same for the slope part of the power law viscosity function, and we now have a complete temperature dependence of this, also based on this reference temperature. We can use one trick in the simulation, since the two regions are not constant. We look at the curve we looked at before. This green line is our viscosity function. We have our Newtonian viscosity here. We have our power law viscosity here. And in simulations, what I do is I calculate both of them, and the one that I use is always the one that is smallest, because you'll notice that during the Newtonian region, the Newtonian viscosity is smaller than the power law, and in the power law region, the power law viscosity is always lower than the Newtonian viscosity. That's it for today, folks. This video was developed in conjunction with the extrusion division by myself, Greg Campbell, and in this case I also produced it.